Welcome back. Last time we were discussing the arc length of a vector function, and we figured out that we could calculate that by taking the integral of the little bits of length along the curve, and we determined that to do that we could take the derivative, the integral of basically the velocity of our function as a function of t. So let's now shift gears and talk about where we're traveling along a curve in either 2-space, 3-space, n-space. And our question is, so we started here at time A, and we ended here at time B. And our question is, can we say, here we are after some time has passed. What's a function for how long we've traveled? For how far, not how long. We know how long, how far it's been that we've traveled since our initial point. So we have our initial point. We want to know how long we've traveled along the curve up until some point in the middle. And so what we'll do is we have a function for that. That's called the arc length function. And so the arc length function says, let's figure out what's the length of the curve from time A to time t. And so we have the formula for calculating the arc length between any 2 points. And here we're going to make this a function between A and t. And so because this is a function between A and t, we need to use a different variable. We need to use a different dummy parameter, in this case u, to represent this the time. So we're going to say this is when u is equal to 0, or sorry, A. This is when u is equal to b. And then we're going to pick just u be equal to t. And then we can talk about the length of the curve from u equals a to u equals t. And that'll become now a function of t. All right. So for example, let's do an example. Here's our friend, the Helix, and we'd like to understand what's the distance that a particle travels from an initial position to any point on the curve. All right, so we have our helix, right? And so here we see, where do we start? Well, if we plug in, if we're looking at the point 1, 0, 0, that's what happens when t is equal to 0. So we're starting at t equals 0. And then as t increases, then we start spinning around and around and around. And we want to know after moving for 5 seconds, how far have we traveled? So for this function, we need to find the arc length function. So we'll replace this r of t by r of u equals cosine of u sine of u comma 1. And so the derivative of this, we take the derivative of each of the pieces. The derivative of cosine is negative sine u squared. The derivative of sine of u is cosine of u squared. And then the derivative of 1 is 0 squared. And so we're starting to like what we're seeing because we see a sine squared plus a cosine squared. So this becomes the integral from u equals 0 to u equals t of 1 du. Square root of 1, which is 1 du. And so this is actually equal to t. So what that means is, oh, wait a minute, what am I doing here? I realize now that this was a t, so I was, in my head, I guess I was taking the derivative earlier. The derivative of t isn't the derivative of u is not equal to 0, the derivative of t is equal to 1. Sorry about that. So this should be 1 plus 1, so it's actually the integral of the square root of 2 du. So the answer is the square root of 2 times t. So what we're saying here, the distance traveled from time 0 to time t is equal to square root of 2 times t. Okay. The reason why I knew I wasn't right is because how high are we going after a time t? Well, this function goes a height, this function has the z value equal to t. And this curve is definitely going further than just the line that goes from 0 up, right? The distance t would represent basically just the vertical line that starts at 0, 0, 0 and goes up the central spindle here of our helix. So this distance that we've traveled, s, is equal to 2 times t, square root of 2 times t. So however long we travel, we're going, the distance that we travel is square root of 2 times that. So we're going to take this and we're going to build on it. We're going to talk about our curve. So as you're driving along a path, sometimes you're going fast and sometimes you're going slow. It might be nice if in our curve, as we're driving, instead of saying that this this curve we're visiting here, this is t equals 0, t equals 1, maybe we stop for a little bit, this is t equals 2, t equals 3. It might be nice that instead of having a function that depends on time, it might be nice to change the rule and say, okay, let's instead have a function, that's not working, that depends on distance. So that when we're at s equals 1, s equals 2, s equals 3, we're basically saying how far along are we on this curve. So what we like is that we'd like that 1 unit in this parameter corresponds to 1 unit in distance instead of representing time. Right? This curve you can follow along in many different ways. What we'd like to do is we'd like to change our parameter that we care about so that 1 unit in the parameter corresponds to 1 unit in distance along the curve. So in order to do that, we need to change whatever this t is, right? We're used to thinking of this as r of t. And what we'd like to do is we'd like to make this instead a function of s. And so what we need to know is how is t as a function of s? So what is t as a function of s? As a function of s. So we're going to figure out what t is as a function of s. If we plug that in for t, we now have an expression that represents the position as a function of s instead of as a function of t. All right, so on the previous slide, we wrote down a function that writes down s as a function of t. So what we need is we need t as a function of s, which is the inverse function. So in this example on the previous page, we figured out that s as a function of t is equal to square root of t. So if we find the inverse function of it, we get that t is equal to s over square root of 2. So now what we do is we say, okay, so we had this function. What's this function? This function was r of t is equal to cosine of t I, cosine of t comma sine of t comma t. And so if we had cosine of t sine of t, t, and we replace t by s over square root of 2, we get r of s is equal to cosine of t, which is cosine of s over root 2, comma sine of t, which is sine of s over root 2, comma t, which is s over root 2. All right, and so what this is a reparametrization with respect to the arc length. Or, in other words, this now says that we've written r as a function of a new parameter s, where one unit in s corresponds to one unit of distance. So if we're putting up mile markers along our curve, we would just have to go to parameter s equals 1, put down the post 1. Go to parameter s equals 2, put down the post 2, and go from there. All right, let's again take a break, and I'll see you shortly. Bye.